Assalamualaikum and a very good morning. Today, our group would like to present our BMIP2324 control system assignment about the second order system in engineering applications. Our group in particular will be focusing on mass spring damper systems. My name is IZZUDDIN and I will be starting with the applications. First of all, a mass spring damper system is a mechanical model that is applied in order to analyze and control vibrations. This kind of model is widely used in engineering applications since many physical systems can be modeled with it. There are three main components in this model: a mass, a spring, and a damper. The spring provides a restoring force when the mass moves, while the damper reduces vibrations and oscillations. Next, I will explain where the control is used in this application. In the mass spring damper system, control is used to reduce unwanted vibrations and help the system return to a stable position quickly after an external force is applied. The input is the external force, while the output is the displacement of the mass. The spring pulls the mass back to its equilibrium position, and the damper absorbs energy to reduce oscillations. Since the system consists of a mass, a spring, and a damper, its behavior is described by a second-order differential equation, making it a classic second-order control system. That is all from me. Now I will pass it to the next member.
Yeah, Assalamualaikum and very good evening. So my name is AHMAD DANISH bin MUZAFAR. So my matrix number is B14241017. So as for today, I will likely to show and presenting about our simulation, which is for our data mass spring damper control system. So as again, I will show you there are two types for our simulation. So the first one will be using the coding, and the second one will be using the simulating. So I will show you the coding first. So as for coding, this is our types of coding. Okay, that's all. So we will save the file. First, we want to run, and then the website will be automatically save the coding. So the calculation has been generated. So as you can see here, the rise time is 1.1977. Transient time will be 1.5484. Settling time will be 1.5484. So for the overshoot will be 30.4890. Then peak time will be 0.4789. Again, it will show you the time, TP, TR, TS, and overshoot. So this is our step response graph. So as for better view, we will put the characteristic and then set the peak response. And as again, rise time. And as again, settling time. And transient time. So for the then we can see the rise time is 0.198, and then the peak time and overshoot also has been generated, and then the transient time also has been generated. Okay, that's all for coding. Now we'll be using the simulate likely for 5 components that we'll be using for the simulation. So the first one, we need to find the step that put up here, and then we will put on the line same with the step for the sum. For the sum, we need to double click it and change for positive and negative. And then we will show the transfer function. As for transfer function, we need to change the numerator and denominator. For the denominator coefficient, we need to put as again like the value that has been put on the coding before. So as I can recall, 1,000, 5,000, and 50,000. Okay, that's all. And then we put the scope here. So for the gain, it will be a feedback. I'm sorry, it's a feedback. So it must conclude, it must include the input, output, and feedback. So as for the gain, we need to the format and then rotate it. Okay, like this. Okay, and then put the then we drag it to the sum, then drag it up here. Okay, and then that's all. We just need to before that we need to decide which stop time we'll be using. So as for our team, we'll be using stop time for 10 seconds. So we can click run, and, and before that it will automatically save. Okay, the simulation has been generated, so we just only click on the scope. Okay, that's for our step response graph. But for finishing, it's better to zero step time, and for sample time, we'll be using a 0.01, and again, okay, there is our step response graph. So this, as you can see from here, I think that's all from me. Thank you very much for your time to watching our presentation. Now I will ending the presentation to my next friend. Thank you.
Assalamualaikum and greeting. My name is Muhammad Aziq bin ZOLKARNAIN. So today I'm going to talk about the system response of the system using step input as the system input. So on the first three line, which talk about defines. In the first line is the define the system mass, which the system mass is 1000 kilograms. So the second line is talk about define about the damping coefficient for our application, which is shock absorber friction. So the third line is define the stiffness of the spring constant. So the next line is numerator and denominator, which our numerator coefficient array is 1, and our denominator array creating the polynomial we had created before is MCK. So we're going to the next line, which is system equal to transfer function. This line is combine numerator and denominator into a system transfer function object. So the next line is step system, which apply an instant jump from 0 to 1. We can say that it is step input, and in this line, it can plot the response. So the next line is grid on, which is turn on the background grid line on the plotted graph for easy reading. So we're going to the next line, info equal to step info system. This line function to calculate all performance metric and save them in a bundle which name info. So the last four line is about extract and print. So for the first line is for peak time, second line rise time, and next line settling time, and last one overshoot. So we can see what our output get from our coding. So if we grid on the grid, we can see the grid on the graph. So for the info output, we can see the output at the comment window here. I think that is all for me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is NAZHIF, and in this section, I will explain how we calculate the tension response characteristic of our mass spring damper suspension system. These characteristics include peak time, settling time, and percent overshoot. They help us evaluate how quickly and smoothly the suspension responds after a disturbance. The system consists of a mass of 1000 kilograms, a damping coefficient of 5000 newton seconds per meter, and a spring constant of 50,000 newtons per meter. From these values, we obtain the transfer function shown here. First, we calculate the natural frequency of the system. The natural frequency depends only on the spring stiffness and the mass. After substituting the values, we obtain a natural frequency of 0.0711 radian per second. Next, we'll calculate the damping ratio. The damping ratio indicates how much oscillation exists in the system. After substitution, the damping ratio is 0.354. Since the damping ratio is less than 1, the system is classified as an underdamped system. This means the output will oscillate before reaching the steady state value, and some overshoot is to be expected. The peak time is the time required for the response to reach its first maximum value. After substituting the values into the equation, the peak time is approximately 0.48 seconds. Settling time is the time required for the response to remain within 2% of its final value. The calculated settling time is approximately 1.60 seconds. And percent overshoot indicates how much the response exceeds its final value before settling. Our calculation gives an overshoot of approximately 30.45%. And this is the output comparison between MATLAB and manual calculation. This graph shows the unit step response of the mass spring damper system. The first peak occurs at approximately 0.48 seconds, which matches our manual calculation. After 1.55 seconds, the response settles near its final value, indicating the settling time. The maximum response exceeds the steady-state value by approximately 30.5%. This confirms the system is underdamped. The manual calculation and MATLAB results are almost identical. The small differences are caused by rounding during manual calculation, whereas MATLAB performs calculation using much higher numerical precision. Overall, the MATLAB simulation successfully verifies the theoretical calculations. Both methods produce nearly identical end values for peak time, settling time, and percent overshoot, confirming that the mathematical model accurately represents the dynamic behavior of the mass spring damper suspension system. Thank you. That's all from me, and I will pass to my teammate.
Assalamualaikum. My name is Muhammad Asif. Today, I will present on stability and steady state error analysis. We will compare the two control systems. The first system is the mass spring damper suspension system, which help reduce the vehicle vibration and improve passenger comfort. The second one is ship roll motion control system, which minimize the rolling motion of a ship caused by wave, improving stability and safety. Next is mathematical modeling. Next, we develop the mathematical modeling for both systems. The equation will convert into transfer function with using the Laplace transform. These transfer functions are important because they allow us to analyze the system performance and behavior. Next is stability analysis. To determine whether the system are stable, we apply the Routh-Hurwitz criterion. This method analyze the characteristic equation and tell us whether the system will remain stable without finding the pole directly. Next is stability result. From the Routh-Hurwitz table, all the value in the first column are positive with no sign changes. Therefore, we can conclude that both the mass spring damper system and the ship roll motion control system are stable. Next is the steady state error analysis. Both systems are classified as type 0 system. This means they have a finite steady state error for a step input, but an infinite error for both ramp and parabolic input. Based on the compression, the mass spring damper suspension system has a smaller steady state error for a step input than the ship roll motion control system. This means it's better tracking performance. However, both systems produce infinite error for ramp and parabolic input. And last, for the conclusion, both systems are stable based on RAFU analysis. However, the mass spring damper suspension system show better steady state error because